Oh, so this is separations homework 3. So this is part A. What we're going to be doing today is going to be drawing schematics of the rectifying, stripping, and feed sections of a distillation column with a total condenser. And from the material balances and envelopes of these column sections, we're going to derive the equations for the rectifying and stripping operating lines and the Q line for the feed. So to start, I already have our distillation column pretty much set. We're going to go ahead and just label our trays, which is usually what a distillation column will have. And we'll say this is N because it's not always 4, it can have more. And through this distillation column, we're going to see two, I guess, directions of material flowing. So we're going to have our vapor moving up while our liquid moves down. And we're basically feeding liquid through our distillation tower, and the vapors that rise will be collected within a condenser. So this is going to be our condenser. Then it's going to come out, and then it's going to have a re-entry and exit. So basically liquid that we do not want within this condenser, so first off, the vapor that goes through will be condensed into liquid, and the stuff we do not want, we will run it back to be able to gain any more vapor that we can out of it, or to just I guess for disposal purposes within this distillation column. And the stuff that we do want, our desired product, is going to be called distillate. That's not the correct spelling, but it's going to be distillate, and it's going to move this way. And yeah, that's our rectifying distillation column. So now what we're going to do is we're going to look at our equation. So we're going to start with defining what our vapor looks like. And our vapor is basically just the accumulation of liquid plus our distillate. And if we see right here, we have our rectifying column. And for this process, we're going to look at it going up, down. So we have our first tray, second, third, then we have N. And then what we're going to do is we're just going to have this defined as N plus 1. We can move forward with making our equation Yn plus 1 times V equals X sub N times our liquid plus X sub D times our distillate. Then we can go ahead and substitute that V in, left with L plus D to get rid of that variable. Just rewrite this. And then we're just going to move on and move that over to get our Yn plus 1 isolated. So then what we're left with is Xn is multiplied by L over L plus D plus XD, which is D over L plus D. Now what we want to look at is a factor that we want to put in is reflux. This is basically what's accounting for out of the distillation tower. So this is going to be equal to R, which is equal to our L over D. And then when we plug that type of concept in, we're just going to go ahead and use a different color, multiply everything by 1 over D. If we just smooth everything out, we essentially get R over R plus 1 x over n plus 1 over r plus 1 times d. And this here is our final equation for that rectifying process. Okay, so now for the stripping section, what we're going to see is we're going to have our column redrawn here. And basically this time, however, what we're going to be having this go through is a reboiler. Just draw this out. And basically what we're going to have is our liquid going down our column, and once it goes through the reboiler, we're going to have the product that we really don't want to go back into the column for it to rise up and condense and go through that cycle till all of that desired product is extracted. And then the stuff we do want, which is our bottoms product, which we'll call B, or add the post-boiled product. And yep, that's pretty much it for the stripping. It's basically the same thing, except when we looked at our rectifying in terms of volume or a vapor, this time we're going to be looking at in terms of liquid from the bottom product. So what we essentially have is L equals R B plus V, which is our vapor and our bottoms. And then like before, we're going to do basically the same thing. We're going to have xn times L, which equals xb times B plus our yn plus 1 times v bar. And then we're going to go ahead and substitute that in. G equals our xb b plus yn plus 1 v bar. And then like before, or at least this time, since our yn plus 1 is on our right side, we want to go ahead and just make that isolated. Yep. Okay, so now what we're going to do is we're going to go ahead and isolate our yn plus 1 a bit further. So what we get is plus v bar over v bar minus rxb over v bar. So like before, for reflux, we were able to use a fraction to cut down our equation. This time we're going to do something similar. What we're going to use is VB, which is our V bar over our B. So for this case, we're going to do is we're going to go ahead and multiply everything by B, or 1 over B. And what we end up with is 1 plus V sub V over VB minus R multiplied by xn minus R 1 over VB times R xb. And this is the equation for our operating line in terms of stripping. Now what we're going to look at is our feed section. So we're going to go ahead and label this. This is going to be our feed going into our column. And basically what we're looking at within the column, we're going to have our vapors. Suppose that's like our little, so we're going to have our vapors moving up, and then we're going to have our liquids coming down. So what we want to just do is, since this is both taking account of both the rectifying and our stripping, we're just going to go ahead and write down both our equations, and we'll use L bar because it's the bottom of the column. And what we're going to have is basically the same exact equations, so I forgot what variable I used. B plus yn plus 1 v bar for our stripping. And then what we're going to have is our yn plus 1 v, which equals xn L plus xd for d. Oh, and then so to develop our envelope, basically what we see in our holistic process, we have our feed going in, and then what we're going to see is our process that we highlighted above, where it goes to our condenser to go back in, and then we're going to have our reboiler or heat exchanger, have our outlet, and then stuff going back in, our distillate B. And if we draw an envelope around our system here, what we see is that this is simply a material balance where we have our inlet and two outlets, which we can then utilize for our equation. And so now what we can do is we can combine our stripping and our rectifying equation to get a little equation where yn plus 1 is multiplied by v minus v bar, which equals xn L minus L bar plus xb times b plus xd times d. Actually, this section right here can just be dumbed down to our composition of feed times our flow. And then what we're going to look at is our liquid fraction of feed, which we use as Q. So if we take our Q times flow, this equals L minus L bar. And so now for our vapors, what we get is 1 minus Q times F, which equals V minus V bar, which looks pretty familiar to what's up here. So what we're going to do is we're going to go ahead and substitute that in. Get times 1 minus Q, which equals X sub N Q F plus our composition feed times F. We can go ahead and cancel out our F, and when we move our 1 minus Q over to isolate our Y sub N plus 1, what we get is Q over 1 minus Q times X sub N plus 1 over 1 minus Q times our composition flow, or composition of our feed. And this right here is our equation for feed. And so what we've successfully done is we've derived the equation for rectifying, stripping, and feed sections of a distillation column.